Hello, my name is Tucker McElroy, and this is my poster with the title Polyspectral Factorization and Prediction for Quadratic Processes. This is joint work with DJ Ghosh and Jemendra Lahiri of Washington University. So my plan is just to give a brief overview of the main points in the poster. The main objective, what we're trying to do here is come up with the formulas, drive the formulas for doing quadratic prediction, quadratic forecasting of time series. Section 2 of the poster has the main objective stated. Equation 1 has an h-step ahead forecast, which it can be expressed in terms of a linear portion. And then there's also coefficients, weighting, products of variables, past and present variables. So that sets out the notation and the objective. Section 3 sets out our notation where we define what the autocumulants are and polyspectra and how those are related to each other. So section 4 is kind of a reformulation of the main goal of the poster. The known formula for linear forecasting is presented in equation 2 in our notation. There's a new result in equation 3, which shows how to do linear forecasting of products of variables. And that's used to kind of recast or reformulate our result. Not a result, but our main decomposition in equation 4. So that sets out our goal to find this quadratic filter. And to do so, we need a couple other results. One is factorization of polyspectra. So this is used later on in the proof. So in section 5, we have some discussion of this topic. In equation 5, there's the expression for the factorization of a polyspectrum if you have a linear process. But here we're interested in nonlinear processes. So we have a more general expression, equation 6, which involves products of functions psi, which are power series in several variables. And the formula involves some group representation theory, which is used to encapsulate the symmetries that are present in the polyspectra. We have an example here with a couple of figures, an example of a Garch-11 process looking at its bispectrum. And the other kind of results we have in section 6 is we look at Wiener-Hopf factorization for infinite arrays, which are Laurent series. So this is kind of like where you have a multivariate spectral density and there's a problem of getting a spectral factorization. So if you let the dimension tend to infinity, you get what we call an infinite array Laurent series. And so that's our new result, is providing that kind of factorization result. So we have some definitions of these objects and the forward and backward factorizations defined, an application. And then basically the main theorem here is that we have we're able to do this factorization under the condition of that the Laurent series 2 array is positive definite. So then in the last section, we put all of these ingredients together. We have assumption P and L. Assumption P is essentially a condition that ensures that the covariance between product pairs of variables, that will actually be positive definite Laurent series 2 array. Assumption L is going to essentially guarantee that the quadratic portion of the filter is non-trivial. And that involves some conditions on the bispectrum. So the formula there in equation 9, that's the main formula of interest. And equation 10 gives you this condition, namely quadratic filter reduces to a linear filter if and only if equation 10 holds. So that's a quick summary of our results. Thank you.